For most of our lives, Pluto was the ninth planet. It was the small, icy world at the edge of the solar system, the lonely outpost beyond Neptune. We memorized it in school. We drew it in diagrams. We accepted it without question. Then in 2006, everything changed. Pluto was demoted, reclassified, stripped of its planetary status. Just like that, it became a dwarf planet. And the explanation sounded simple. It didn't meet the new definition of a planet. But here's what most people don't realize. Pluto didn't change. Our definition did. As astronomers discovered more large objects beyond Neptune, worlds similar to Pluto, the solar system suddenly became crowded. If Pluto was a planet, then several others might have to be called planets too. Instead of expanding the list, scientists rewrote the rules. Pluto failed one requirement. It hasn't cleared its orbit. And that single technical phrase reshaped how we view the outer solar system. But when NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed something extraordinary. Towering ice mountains, vast nitrogen glaciers, a beating, heart-shaped plain, a complex blue atmosphere, possible underground oceans. This wasn't a forgotten rock. It was a dynamic world. So was Pluto truly downgraded because of science? Or because our old categories couldn't handle what we were discovering? Pluto is not what you think. And the story behind it is far more complicated than we were ever taught. When Clyde Tombaugh discovered Pluto in 1930, it wasn't just another astronomical observation. It was a victory. For decades, astronomers had suspected that something was tugging on the outer planets. Neptune and Uranus didn't seem to move exactly as predicted. Their orbits hinted at an unseen gravitational influence, a hidden world lurking beyond the known edge of the solar system. Percival Lowell called it Planet X, and he dedicated years of his life to finding it. After Lowell's death, the search continued. At the Lowell Observatory in Arizona, a young farm boy named Clyde Tombaugh was hired to systematically photograph the sky. Night after night, he compared glass photographic plates, looking for a tiny point of light that shifted position against the background stars. On February 18, 1930, he found it, a faint speck, moving slowly, consistently. Pluto. It was immediately celebrated as the long-awaited Planet X. Newspapers across the world announced the discovery of the ninth planet. School textbooks were updated. Pluto became part of humanity's cosmic identity. But almost immediately, there was a quiet problem. Pluto was small, very small. At first, astronomers assumed it must be roughly the size of Earth, maybe even larger. That would explain the gravitational disturbances in Neptune's orbit. But as measurements improved over the decades, Pluto kept shrinking. By the 1950s, it was clear that Pluto was nowhere near Earth-sized. By the 1970s, scientists realized it was smaller than our moon. That created a serious issue. If Pluto was so tiny, how could it possibly be responsible for disturbing the orbits of the outer planets? The answer was uncomfortable. It couldn't. Eventually, more precise measurements of Neptune's mass revealed something surprising. There was no mysterious gravitational anomaly after all. The original calculations had simply been slightly off. There was no need for a massive Planet X to explain anything. Pluto hadn't been discovered because it was causing measurable gravitational effects. It had been discovered almost by accident. That doesn't make the discovery less impressive. Tombaugh's work was still extraordinary. But it does mean Pluto wasn't what astronomers originally thought it was. And that was only the beginning. As telescopes improved, astronomers began discovering more icy objects beyond Neptune. The Kuiper Belt, a vast ring of frozen debris at the outer edge of the solar system, started to reveal itself. Pluto wasn't alone out there. It wasn't a singular frontier world. It was part of a population. In 1992, the first confirmed Kuiper Belt object after Pluto was discovered. Then more followed. Dozens, hundreds, thousands. These weren't asteroids like those between Mars and Jupiter. They were icy worlds. Some were only a few kilometers wide. Others were hundreds of kilometers across. Then came the discovery that truly shook everything. In 2005, astronomers found Eris. Eris was massive, at least as large as Pluto, possibly even slightly larger. It orbited the Sun far beyond Pluto, in an even more distant and elongated path. If Pluto was a planet, then Eris had to be one too. And if Eris was a planet, what about the other large Kuiper Belt objects? Suddenly, the solar system risked expanding from 9 planets to 12, or 20, or 50. This wasn't just a classification problem. It was philosophical. What is a planet? For decades, the definition had been informal. A planet was simply a large body orbiting the Sun. Pluto fit that description. But as more objects were discovered, the simplicity of that definition collapsed. Astronomers were forced to confront a difficult choice: either accept that the solar system had dozens of planets or redefine the word planet. In 2006, the International Astronomical Union met in Prague. After heated debates, they voted on a new official definition. To be a planet, an object must 1. Orbit the Sun. 2. Be massive enough for its gravity to pull it into a nearly round shape. 3. Have cleared its orbit of other debris. Pluto met the first 2 conditions. It failed the third. Pluto shares its orbital zone with countless other Kuiper Belt objects. It has not gravitationally dominated its neighborhood. It hasn't cleared its orbit the way Earth, Jupiter, or Neptune have. So Pluto was reclassified. It became a dwarf planet. The reaction was immediate and emotional. People felt betrayed. Pluto had been part of our cultural framework for generations. Children learned about 9 planets. Pluto was the underdog, the distant mystery. Its demotion felt personal. But scientifically, the change reflected something important. We were discovering that the solar system was far more complex than we once imagined. Pluto wasn't being diminished, it was being understood. And understanding it would require something humanity had never done before. We would have to go there. For 75 years after its discovery, Pluto remained a blurry dot of light. Even the Hubble Space Telescope could only resolve faint surface variations. We knew its orbit. We knew its size. We knew it had a large moon named Charon, discovered in 1978. But what did Pluto actually look like? What kind of world was it? That question lingered for decades until NASA launched New Horizons in 2006. At the time of launch, Pluto was still considered a planet. By the time New Horizons reached it, Pluto had already been demoted. That coincidence would turn out to be poetic, because what New Horizons revealed would challenge everything we thought we knew. As the spacecraft approached Pluto in July 2015, the first close-up images began to arrive. And what they showed was not a frozen, inactive rock. It was a living world. Towering mountains made of water ice rose thousands of meters high. Vast plains of nitrogen ice stretched across the surface. There were signs of flowing glaciers. There were hints of geological activity. There was a complex layered atmosphere glowing blue in the sunlight. Pluto wasn't a static relic. It was dynamic. And that forced scientists to ask an even deeper question. If Pluto behaves like a planet, if it has geology, weather, mountains, atmosphere, if it has a large moon system, if it may even harbor a subsurface ocean, then what exactly makes something a planet? The 2006 definition focused heavily on orbital dominance, the idea that a planet must clear its neighborhood. But critics argue that this criterion is arbitrary. After all, Earth shares its orbit with thousands of near-Earth asteroids. Jupiter shares its orbit with Trojan asteroids. No orbit is perfectly cleared. The difference is one of scale. Earth and Jupiter are gravitationally dominant. Pluto is not, but does dominance define identity? That question has divided astronomers ever since. Some planetary scientists argue that Pluto should be considered a planet based on its intrinsic properties, its geology, atmosphere, complexity. They suggest a geophysical definition of planet. If it's round and geologically active, it qualifies. Under that definition, Pluto would absolutely be a planet. So would many moons, including Europa, Titan, and even our own moon. The debate isn't over. And perhaps that's the most important part of Pluto's story. Pluto didn't just change categories. It forced us to rethink how we categorize the universe. It exposed the limits of simple definitions in a complex cosmos, because the more we look outward, the more we realize that nature doesn't follow our tidy labels. Pluto is not what we were taught in school. It is neither the mysterious giant planet X nor a meaningless frozen rock. It is a member of a vast family of icy worlds, a gateway to understanding the Kuiper Belt, planetary formation, and the architecture of solar systems across the galaxy. And as we continue exploring, Pluto may turn out to be one of the most important objects ever discovered. Not because it was the 9th planet, but because it showed us how much we still have to learn. If Pluto forced us to question definitions, the Kuiper Belt forced us to question scale. For most of the 20th century, the solar system appeared clean and orderly in textbooks. 4 small rocky planets near the Sun, an asteroid belt, 4 giant planets, then Pluto, the distant outlier. But that tidy structure was an illusion created by limited observation. Beyond Neptune lies a vast region extending billions of kilometers outward. This region, now known as the Kuiper Belt, is not empty space. It is filled with remnants from the early solar system. Frozen objects made of rock and ice that never merged into a full-sized planet. Pluto was the first known member of this population, but it is not the largest by much, and it is far from alone. The Kuiper Belt begins just beyond Neptune's orbit, at about 30 astronomical units from the Sun, and stretches outward to roughly 50 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. That means Pluto resides tens of times farther from the Sun than Earth does. At such distances, sunlight is weak. temperatures plunged to around -220 degrees Celsius. Volatile substances like nitrogen, methane, and carbon monoxide freeze solid. These conditions preserved ancient material from the formation of the solar system 4.5 billion years ago. The Kuiper Belt is a fossil record, and Pluto is one of its most accessible representatives. When the Kuiper Belt was confirmed in the early 1990s, it changed everything. Suddenly, Pluto wasn't an isolated oddity. It was the brightest member of an entire class of objects, and those objects came in variety. Some are relatively small, only tens of kilometers across. Others approach Pluto's size. Several are spherical, meaning they have enough gravity to pull themselves into round shapes, just like Pluto. Eris, discovered in 2005, was one of these. At first, measurements suggested Eris was slightly larger than Pluto. That single detail created an identity crisis for planetary science. If Pluto was a planet, Eris had to be one too. But Eris was only the beginning. Makemake, Haumea, Quaoar, Sedna. Each new discovery expanded the known boundaries of the solar system. Each one blurred the line between planet and minor body. The solar system wasn't neat. It was layered. Pluto occupies a special position within this belt. It is what astronomers call a Plutino, meaning it is in a 2 to 3 orbital resonance with Neptune. For every 2 orbits Pluto makes around the Sun, Neptune makes 3. This gravitational resonance protects Pluto from ever colliding with Neptune, even though their orbits cross in 3-dimensional space. That crossing alone challenges classroom diagrams. Pluto's orbit is highly elliptical and tilted by about 17 degrees relative to the plane of the solar system. At times, it comes closer to the Sun than Neptune does. A true planet, according to older assumptions, was expected to follow a near-circular orbit, aligned with the solar system's plane. Pluto does not. Its strange orbit suggests a chaotic past, a history of gravitational interactions during the early formation of the solar system. One leading theory, known as the Nice model, proposes that the giant planets once migrated from their original positions. As Jupiter, Saturn, Uranus, and Neptune shifted, their gravitational forces scattered countless icy objects outward. Some were ejected from the solar system entirely. Others were trapped in resonances. Pluto may have been one of these displaced bodies, caught in Neptune's gravitational influence and locked into its current orbit. If this model is correct, Pluto isn't just an object at the edge of the solar system. It is evidence of planetary migration. It is proof that the early solar system was violent and unstable. This changes the narrative entirely. Pluto was once thought to be the final distant planet. Now it appears to be a survivor of gravitational upheaval. Its composition supports this idea. Pluto is made of a mixture of rock and ice, roughly 2/3 rock, 1/3 ice. That means it is denser than pure ice, but less dense than Earth. Its surface is covered in frozen nitrogen, methane, and carbon monoxide, volatile compounds that sublimate and refreeze as Pluto moves along its elongated orbit. When Pluto approaches perihelion, its closest point to the Sun, sunlight warms its surface slightly. Some of the nitrogen ice sublimates into a thin atmosphere. As Pluto moves farther away, that atmosphere freezes and falls back to the surface. Pluto breathes, not in the biological sense, but in a seasonal cycle spanning centuries. This dynamic behavior shocked scientists when New Horizons arrived. For decades, Pluto had been assumed to be inert, too small and too cold to sustain geological activity. But the heart-shaped region, known as Sputnik Planitia, told a different story. Sputnik Planitia is a vast basin filled with nitrogen ice. It is smooth, young, and geologically active. The surface shows evidence of convection, slow overturning of ice driven by internal heat. For convection to occur, there must be energy. Where does that energy come from? Pluto is small. It does not experience tidal heating like Jupiter's moon Europa. It does not have the mass of Earth. Yet models suggest Pluto may retain residual heat from radioactive decay within its rocky core. There is even evidence suggesting a possible subsurface ocean beneath its icy crust. If Pluto has an ocean, even a partially frozen one, then it is far more complex than a typical dwarf planet. It becomes a world with internal structure. Pluto also has a remarkable moon system. Charon, its largest moon, is so massive relative to Pluto that the two bodies orbit a shared center of mass located outside Pluto's surface. In practical terms, this means Pluto and Charon behave almost like a binary planet system. No other planet in the solar system shares such an arrangement. Charon itself is geologically interesting, with vast canyons and dark polar regions. Beyond Charon, Pluto has 4 smaller moons: Styx, Nix, Kerberos, and Hydra. Their orbits are chaotic, likely influenced by the complex gravitational interactions of the system. This architecture resembles scaled-down planetary systems. Pluto is not simply a lonely rock. It is a system, and systems imply history. The leading theory suggests that Pluto and Charon formed after a massive collision in the early solar system. A large object may have struck Pluto, ejecting debris that coalesced into Charon. This scenario mirrors the leading theory for the formation of Earth's moon. If that is the case, Pluto experienced cataclysmic events similar to those that shaped Earth. Once again, the idea of Pluto as a minor leftover becomes harder to sustain. It is ancient, it is structured, it is active, it has a complex orbital story, it has a moon system, it may have an ocean. Yet under the 2006 definition, it is not a planet. Part 2 of Pluto's story reveals something deeper than classification debates. It reveals that the outer solar system is not a boundary, it is a frontier. The Kuiper Belt is vast and largely unexplored. Pluto is just one member of a hidden population of worlds, and as we discover more exoplanets around other stars, many of them appear similar in size to Pluto, small, icy bodies far from their stars. Understanding Pluto may help us understand those distant systems. Pluto is not the end of the solar system. It is the beginning of understanding a much larger structure. The question is no longer whether Pluto deserves the title of planet. The question is whether our definition of planet is too small to describe what we are discovering. Because the deeper we explore the Kuiper Belt, the clearer it becomes. Pluto is not an exception. It is a prototype, and prototypes are rarely simple. When New Horizons launched in January 2006, Pluto was still officially the 9th planet. By the time the spacecraft reached its destination in July 2015, Pluto had already been reclassified as a dwarf planet. In that span of 9 years, something remarkable happened. Our definition changed before our understanding did. New Horizons was not sent to Pluto because it was controversial. It was sent because Pluto was unknown. For 85 years after its discovery, Pluto had remained a blur. Even the Hubble Space Telescope could only reveal light and dark patches across its surface. We had rough measurements of its size, its mass, its orbit. We knew it had a large moon, but we had never seen it up close. The mission itself was ambitious. Pluto is nearly 6 billion kilometers from the Sun. It takes light more than 4 hours to travel from Earth to Pluto. At the time of launch, New Horizons was the fastest spacecraft ever sent from Earth. Even at that speed, it would take 9.5 years to reach its target. There would be no second chances. Unlike missions to Mars or Jupiter, New Horizons could not slow down and enter orbit. There simply wasn't enough fuel. It would fly past Pluto at nearly 14 kilometers per second, collecting as much data as possible in a brief window of hours. Everything depended on timing and precision. As the spacecraft approached in early 2015, the first images began to sharpen. What had once been a fuzzy disk slowly resolved into a world. And then came the heart. The most iconic image of Pluto revealed a bright, heart-shaped region dominating one hemisphere. It was instantly recognizable, emotionally charged, almost symbolic. But scientifically, it was astonishing. This feature, later named Tombaugh Regio in honor of Pluto's discoverer, was not just decorative. Its western half, Sputnik Planitia, was a vast basin filled with nitrogen ice. It was smooth, young, geologically active. There were no impact craters in large portions of this region. That was shocking. Impact craters accumulate over billions of years. A surface covered in craters is old. A smooth surface suggests renewal. Recent geological activity erasing older marks. Pluto, the supposedly frozen relic at the edge of the solar system, had a young surface. Mountains rose at the edge of Sputnik Planitia. Some reached heights of 3,500 meters. These were not rocky peaks like those on Earth. They were made of water ice, which at Pluto's temperatures is as hard as granite. Water ice is the bedrock of Pluto. Above and around it lay layers of more volatile ices: nitrogen, methane, carbon monoxide. Materials that would be gases closer to the Sun. The nitrogen plains showed patterns resembling convection cells. Polygons stretching across the surface suggested that the ice was slowly overturning, driven by heat from below. This implied an internal energy source. Pluto was not dead. The discovery of potential cryovolcanoes added to the mystery. These icy volcanoes may have erupted mixtures of water and ammonia in the distant past, reshaping the landscape. How could such a small body retain enough heat to drive activity? Radioactive decay within its rocky core could provide a modest source of energy. But some models suggested something more intriguing: a subsurface ocean. If Pluto possesses a layer of liquid water beneath its icy crust, insulated by layers of ice and antifreeze compounds like ammonia, it would place Pluto among a select group of potentially ocean-bearing worlds in the solar system: Europa, Enceladus, Titan, and now, perhaps, Pluto. The atmosphere of Pluto was equally surprising. New Horizons observed a thin atmosphere composed primarily of nitrogen, with traces of methane and carbon monoxide. As sunlight passed through it, the atmosphere scattered blue light, creating a faint blue haze around the planet's limb. This was unexpected. Pluto is too small to hold a thick atmosphere for long periods. Yet its atmosphere exists in a delicate seasonal cycle. As Pluto approaches the Sun, nitrogen ice sublimates into gas, forming an atmosphere. As it recedes, that atmosphere freezes and falls back to the surface like snow. Pluto experiences seasons that last decades. Its climate is slow, dramatic, and extreme. Then there was Charon. As New Horizons flew past, it revealed a world almost as fascinating as Pluto itself. Charon's surface displayed enormous canyons stretching over 1,600 kilometers, deeper and longer than the Grand Canyon. There were smooth plains suggesting resurfacing events, and a mysterious dark red region at its north pole, likely formed from methane escaping Pluto and freezing onto Charon's surface. The Pluto-Charon system did not resemble a simple planet-moon pair. It looked like a binary world. The center of mass between them lies outside Pluto's surface. They are gravitational partners, locked in mutual orbit, always showing the same face to each other. Their formation likely involved a massive collision early in the solar system's history, a violent impact that ejected debris, later forming Charon. In many ways, this mirrors the leading theory of how Earth's moon formed. Pluto's story became more complex with every image. Instead of confirming Pluto as a minor object, New Horizons elevated it into one of the most intriguing worlds ever explored. And this raised an uncomfortable tension. If Pluto is geologically active, if it has complex weather cycles, if it may harbor an ocean, if it has a sophisticated moon system, what exactly separates it from planets we already accept? Size, orbital dominance, or familiarity? Pluto forced planetary science into a philosophical corner. The 2006 definition focused on clearing one's orbit, a measure of gravitational dominance. But this criterion is tied to location and environment, not intrinsic properties. If Earth were placed in the Kuiper Belt, it would not clear its orbit either. Context matters. Pluto's demotion was not about what it is, it was about where it is. New Horizons revealed something else. Pluto is not static in time. The absence of craters in some regions suggests resurfacing within the last 100 million years, possibly even more recently. That is astonishing for a body so small and so distant. For comparison, Earth's continents are billions of years old. Mars shows geological activity that may still be ongoing, but Pluto, once assumed frozen and inert, displays signs of renewal. It challenges the assumption that size alone determines complexity. Small worlds can be active. Distant worlds can be dynamic. Pluto is not a relic. It is a laboratory. The mission also revealed subtle atmospheric escape. Pluto's weak gravity allows some of its atmospheric particles to drift into space. Over millions of years, this process could significantly alter its surface composition. Pluto is evolving, not rapidly, but measurably. When New Horizons completed its flyby, it continued outward into the Kuiper Belt, eventually visiting another object named Arrokoth in 2019. Arrokoth was far more primitive, a contact binary made of two lobes gently fused together. Compared to Arrokoth, Pluto looked advanced, complex, reshaped. This contrast highlighted Pluto's uniqueness within the Kuiper Belt. It is not just another icy rock. It is one of the largest, most structured members of its population. New Horizons did more than take pictures. It transformed Pluto from abstraction into reality. Before 2015, Pluto was a dot. After 2015, It was a world, and that transformation reshaped the debate. The question was no longer whether Pluto is interesting. It was whether our labels are sufficient. Part 3 of Pluto's story is not about demotion. It is about revelation, because the closer we looked, the stranger Pluto became. It is not what we were taught. It is colder, more dynamic, more complex, more alive than expected. And perhaps that is the real lesson. The universe rarely conforms to the categories we create. Pluto didn't shrink when it was reclassified. It expanded, not in size, but in meaning. If the first chapters of Pluto's story were about discovery and redefinition, this chapter is about something deeper. Why did the debate become so emotional? Why did a technical vote at an astronomical conference spark outrage across the world? Because Pluto was never just a scientific object, it was cultural. For 76 years, Pluto was the 9th planet. Entire generations grew up memorizing its name. Teachers used it as a symbol of the unknown. It represented the outer edge of our cosmic map, and then it was taken away. But here's what most people don't realize. The vote that reclassified Pluto was not unanimous. It wasn't even attended by most professional astronomers. In 2006, at the International Astronomical Union meeting in Prague, only about 400 of the roughly 10,000 members were present for the final vote. That means less than 5% of the organization decided Pluto's fate. That statistic alone fueled skepticism. Critics argued that such a monumental decision, redefining the solar system, should have involved broader participation. Others pointed out that the new definition only applied to objects orbiting the Sun, meaning it excluded exoplanets orbiting other stars. If the definition doesn't apply universally, is it truly fundamental? The core issue centered on the third criterion: clearing the orbit. To clear its orbit means that a planet has become gravitationally dominant in its orbital zone. It has either absorbed or scattered most other objects of similar size. Earth has done this. Jupiter has done this spectacularly. Pluto has not. But some planetary scientists argue that this standard is flawed. For one thing, no orbit is ever completely clear. Earth shares space with thousands of near-Earth asteroids. Jupiter shares its orbit with Trojan asteroids. Even Neptune, whose gravity influences Pluto, shares its region with countless smaller objects. The difference is relative dominance. Earth outweighs the total mass of other objects in its orbital zone by a massive factor. Pluto does not. But is gravitational dominance the defining feature of a planet? Or is it simply a measure of location and environment? If you moved Earth to Pluto's position in the Kuiper Belt, it might not clear its orbit either. There is simply too much material in that region. That raises a provocative idea. Maybe the classification says more about orbital neighborhood than intrinsic nature. Pluto is round. It has differentiated layers, a core, mantle, crust. It has geology. It has an atmosphere. It has a complex moon system. If we discovered Pluto orbiting another star far from any large neighbors, would we hesitate to call it an exoplanet? Probably not. In fact, astronomers routinely classify exoplanets smaller than Pluto as planets based on size and orbit around a star, without applying the clearing the orbit rule. That inconsistency troubles some scientists. A growing number advocate for a geophysical definition of planet, one based on physical characteristics rather than orbital context. Under this definition, Any round body that has sufficient gravity to shape itself into a sphere would qualify. If that standard were adopted, the solar system would gain dozens of planets overnight. Pluto would be restored. So would Eris, Haumea, Makemake. Even large moons like Titan, Europa, and Ganymede would qualify. The solar system would become more complex, but perhaps more honest. The resistance to that idea isn't purely scientific. It's practical. Imagine teaching children that the solar system has over 100 planets. Imagine constantly updating the list as new Kuiper Belt objects are discovered. There is comfort in simplicity. 9 planets was simple. 8 planets is even simpler. But simplicity isn't the universe's priority. There's another layer to this debate that often goes unspoken: hierarchy. Calling Pluto a dwarf planet feels like diminishing it. The word dwarf implies inferiority. It suggests something incomplete. But in astronomy, dwarf does not mean insignificant. White dwarfs are among the densest objects in the universe. Dwarf galaxies contain billions of stars. Dwarf planets are simply bodies that share characteristics with planets, but exist in crowded neighborhoods. The term is descriptive, not insulting. Yet emotionally, it felt like exile. Part of that emotional reaction reveals something profound about human psychology. We form attachments to categories. We like order. We like clean lists. Pluto disrupted that order. When Eris was discovered and appeared larger than Pluto, astronomers faced a crossroads: either accept many more planets or narrow the definition. They chose narrowing. Some argue that this was a conservative decision, an attempt to maintain stability rather than embrace expansion. Others argue it was necessary to prevent the term planet from losing meaning. But meaning evolves. Before Copernicus, Earth wasn't considered a planet at all. It was the center of everything. After heliocentrism, Earth joined the planetary ranks. Before the discovery of Ceres in 1801, there were only 7 known planets, including the Sun and Moon in ancient classifications. When Ceres was found between Mars and Jupiter, it was initially called a planet. Then dozens more similar bodies were discovered. Ceres was reclassified as an asteroid. Sound familiar? History repeats. Pluto followed a similar path. Discovered in isolation, celebrated as a planet, later revealed to be part of a larger population, reclassified accordingly. The difference is cultural scale. Ceres' demotion in the 19th century did not cause global outrage. Pluto's did, because by the 21st century, science was part of mass media culture. Pluto wasn't just an astronomical object. It was a character in humanity's cosmic story. Part 4 of Pluto's story is not about ice or orbit. It's about identity. Who decides what a planet is? Is it a vote, a definition, a consensus? Or is it something more fluid, shaped by discovery and reinterpretation? Even today, the debate continues. Some planetary scientists, including members of the New Horizons team, argue openly for Pluto's restoration as a planet under a geophysical definition. Others defend the IAU's decision as necessary and scientifically sound. The disagreement is not trivial. It reflects 2 philosophies of classification. One prioritizes orbital dynamics. The other prioritizes intrinsic properties. Pluto sits at the intersection of those philosophies. It is too large and complex to ignore, too embedded in a population to dominate, too culturally significant to fade quietly. Perhaps the real lesson of Pluto is not whether it deserves the title of planet. Perhaps it is this: science is not static. Definitions are not eternal. They evolve as knowledge expands. Pluto didn't shrink in 2006. Our understanding grew. And when understanding grows, categories shift. Pluto forced astronomers to confront the fact that the solar system is not a tidy row of neatly separated worlds. It is layered, dynamic, crowded, and complex. And sometimes, when complexity increases, simplicity must give way. The debate over Pluto is not about lies. It's about limits. The limits of language, the limits of classification, the limits of how we describe a universe that refuses to fit into small boxes. Pluto is not what you think, not because someone deceived us, but because reality turned out to be more complicated than the diagram in a textbook. And complexity is never comfortable, but it is always closer to the truth. If Pluto's story has been about discovery, reclassification, and revelation, then this chapter must confront the deeper question: why does it matter? Why does the status of a distant icy world, billions of kilometers away, generate debate at all? Because Pluto is not just about planetary labels. It is about how we understand the architecture of our solar system, and by extension, how we understand planetary systems everywhere. Pluto sits in a region that was once thought to be empty. Before the 1990s, Neptune marked the practical edge of the known solar system. Beyond it lay darkness. Pluto appeared to be the final, lonely body orbiting the Sun. But the conformation of the Kuiper Belt changed that perspective permanently. The outer solar system is not an edge. It is a reservoir. It is filled with primordial material, objects that never merged into larger planets during the chaotic formation of the solar system. These bodies are time capsules. They preserve clues about how planets form, migrate, and sometimes fail to grow. Pluto is one of the largest survivors of that early era. In a sense, Pluto represents an interrupted planet. It grew large enough to become spherical. It differentiated internally, forming a rocky core and icy mantle. It developed geological complexity, but it never became dominant. It never cleared its orbital neighborhood. It never captured thick hydrogen or helium atmospheres like Neptune. It stopped mid-transformation, and that makes it scientifically invaluable. To understand Pluto is to understand the boundary between small bodies and full-fledged planets. This boundary is not sharp, it is gradual. Pluto's mass is about 0.2% of Earth's. That sounds small, and it is. But mass alone does not dictate complexity. Pluto has mountains, plains, possible cryovolcanism, and atmospheric cycles. Compare that to Mercury, which is far larger but geologically quieter today. Size does not equal simplicity. Another reason Pluto matters is orbital dynamics. The structure of the Kuiper Belt and Pluto's resonance with Neptune supports the idea that the giant planets migrated early in solar system history. The NICE model suggests that Jupiter, Saturn, Uranus, and Neptune did not form exactly where they are now. Their gravitational interactions scattered debris outward and reshaped the architecture of the outer system. Pluto's current orbit, tilted and elongated, may be a fossil record of that migration. If the giant planets moved, they would have disturbed countless icy bodies. Some would be ejected into deep space. Others would be trapped in resonances, like Pluto. This means Pluto is not just an isolated object. It is evidence of planetary instability, and instability in early planetary systems appears to be common. Observations of exoplanets show that many giant planets orbit extremely close to their stars. Far closer than Mercury orbits the Sun. These hot Jupiters likely migrated inward from more distant formation zones. Planetary systems are not static. They rearrange themselves. Pluto's strange orbit is a reminder that our own solar system likely experienced similar upheavals. Understanding Pluto helps refine those models. But Pluto's importance goes beyond orbital mechanics. It challenges assumptions about habitability and internal heat. Pluto is small and distant. By traditional thinking, it should have cooled completely billions of years ago. Without tidal heating like Europa experiences, without proximity to the Sun, Pluto should be frozen solid throughout. Yet models suggest it may harbor a subsurface ocean. If confirmed, that possibility expands the range of environments where liquid water might exist. Liquid water is one of the key ingredients for life as we know it. Finding it beneath the icy crust of a distant dwarf planet forces us to reconsider the limits of habitable environments. Pluto is not a likely home for life, but its internal complexity suggests that small worlds may be more dynamic than we once believed. And if small icy bodies can retain oceans, then the outer solar systems of other stars may be filled with potentially ocean-bearing worlds. The discovery of Arrokoth by New Horizons after the Pluto flyby added another layer to this story. Arrokoth is far more primitive, a contact binary made of two lobes gently fused together. It appears to be largely unaltered since the formation of the solar system. Comparing Arrokoth to Pluto reveals something fascinating. Pluto is evolved. Arrokoth is primordial. Both formed in the same general region, but their evolutionary paths diverged dramatically. Pluto experienced internal heating, differentiation, resurfacing, atmospheric cycles. Arrokoth remained cold and unchanged. This contrast provides a natural laboratory for understanding how initial conditions and mass determine planetary outcomes. Pluto sits near a tipping point. Slightly smaller, and it might resemble Arrokoth. Slightly larger, and it might resemble Triton, Neptune's captured moon, which shows even more dramatic geological activity. Pluto occupies the threshold between inert debris and active world. That threshold is scientifically rich. There is also a deeper philosophical lesson embedded in Pluto's journey. When Pluto was demoted, many people framed it as loss. But from a scientific perspective, Pluto gained context. It went from being the 9th planet to being the largest member of a vast, newly recognized region. Instead of standing alone at the edge of the solar system, Pluto became the gateway to the Kuiper Belt. It shifted from isolation to belonging. That shift mirrors how science often progresses. Discoveries rarely shrink the universe. They expand it. Pluto did not become less important after 2006. It became part of a larger narrative. And that narrative is still unfolding. Future missions may one day return to Pluto, perhaps even orbit it. Advanced telescopes may detect seasonal changes in its atmosphere. Improved models may confirm or reject the presence of a subsurface ocean. Pluto is not finished surprising us. But perhaps the most important takeaway is this. The solar system is not a tidy set of categories. It is a continuum. Rocky worlds blend into icy bodies. Large moons resemble small planets. Dwarf planets share characteristics with full-size ones. Pluto exists at the boundary of these categories, and boundaries are where understanding deepens. Part 5 of Pluto's story is not about defending or attacking a definition. It is about recognizing that classification is a tool, not a truth. The universe does not care what we call Pluto. It remains what it is, an icy world with mountains of water ice, nitrogen glaciers, a beating heart-shaped plain, a dynamic atmosphere, and perhaps an ocean beneath its crust. The debate over its planetary status may continue for decades, but regardless of label, Pluto stands as one of the most intriguing worlds in our solar system. It forced us to reconsider what a planet is. It revealed that the outer solar system is alive with complexity, and it reminded us that the farther we look, the more the universe refuses to fit into simple definitions. Pluto is not what you think, not because we were lied to, but because the story was incomplete, and now we are still writing the rest. If Pluto has taught us anything so far, it is that scale does not determine significance. For decades, we assumed the outer solar system was a quiet graveyard, a place where frozen leftovers drifted in darkness. Pluto was treated as the smallest, least important member of the planetary lineup. It was distant, dim, easy to ignore. But the deeper we look, the more Pluto reveals something unexpected. Small worlds can carry enormous meaning. Pluto forces us to reconsider a bias that has shaped planetary science for generations. The idea that bigger equals more important. The gas giants dominate visually. Jupiter commands attention with its size and storms. Saturn's rings dazzle. Even Neptune and Uranus, far away and cold, are massive and unmistakable. Pluto, by contrast, is tiny. Its diameter is just 2,377 kilometers, smaller than Earth's moon. If you place Pluto across the continental United States, it would barely stretch from coast to coast. Yet complexity does not scale linearly with size. Despite its small mass, Pluto has a differentiated interior, meaning its materials separated into layers. It has a rocky core, likely surrounded by a mantle of water ice and a crust composed of volatile ices. This internal structure mirrors that of full-size planets. Differentiation requires heat. Heat requires energy, and energy requires history. Pluto did not simply freeze into existence. It evolved, and that evolution carries clues about planetary formation that larger planets sometimes obscure. Consider this. In the early solar system, countless planetesimals, small building blocks of planets, collided and merged. Some grew into the rocky planets of the inner system. Some became the gas giants. Many remained scattered fragments. Pluto represents a middle ground, a world that grew large enough to become complex, but not large enough to dominate. Studying such intermediate bodies helps scientists understand the transition from debris to planet. Where does a world begin? At what size does internal heat persist? At what threshold does geology activate? Pluto provides data points near those thresholds. Its nitrogen glaciers demonstrate that even extremely cold environments can experience convection. Its possible cryovolcanoes show that liquid water-ammonia mixtures can erupt in places far removed from sunlight. This expands our view of planetary activity. Activity is not reserved for warm worlds near stars. It can occur in distant, icy realms, and this matters when we look beyond our solar system. Exoplanet surveys have revealed thousands of worlds orbiting other stars. Many are between Earth and Neptune in size, a category sometimes called mini-Neptunes or super-Earths. Others are likely icy bodies in outer regions of their systems. Pluto may resemble the most common type of planetary object in the galaxy. Understanding Pluto may therefore help interpret exoplanetary systems. Another reason Pluto matters lies in its atmosphere. Despite its weak gravity, Pluto maintains a thin atmosphere that interacts dynamically with its surface. When it approaches perihelion, nitrogen ice sublimates and forms a temporary gaseous envelope. As it recedes, that atmosphere collapses and freezes. This cycle suggests a delicate balance between gravity, temperature, and volatility. In planetary science, these balances determine whether atmospheres persist or escape. Mars lost much of its atmosphere over time. Earth retained its thick one. Titan holds onto a nitrogen-rich atmosphere despite being smaller than Mercury. Pluto's tenuous atmosphere is part of this broader pattern, a data point in understanding atmospheric survival at extreme distances. There is also the matter of surface chemistry. New Horizons detected complex organic molecules, tholins, on Pluto's surface. These reddish compounds form when ultraviolet radiation interacts with methane and nitrogen. Tholins are not life, but they are prebiotic chemistry. They represent the kind of organic complexity that can arise naturally in cold, irradiated environments. Pluto's reddish hues hint at chemical processes that may be common in outer solar systems. And then there is Charon. The Pluto-Charon system challenges our concept of moons and planets. Because their center of mass lies outside Pluto, some scientists argue that they function as a binary planet system. Binary stars are common. Binary planets are rare, at least in our system. The gravitational dance between Pluto and Charon offers insights into tidal locking, orbital resonance, and mutual evolution. Charon always shows the same face to Pluto, and Pluto does the same to Charon. They are permanently locked in orientation. This arrangement provides a stable laboratory for studying gravitational coupling. Beyond Charon lie Pluto's smaller moons, Styx, Nix, Kerberos, Hydra. Their irregular shapes and chaotic rotations suggest a violent origin, likely from debris of a massive collision. This collision scenario parallels Earth's moon-forming impact. Pluto's history may not be peaceful. It may be shaped by early chaos, frozen into present form. When you consider all of this, geology, atmosphere, chemistry, moons, possible ocean, the idea that Pluto is lesser feels misleading. It is not less complex. It is not less dynamic. It is simply smaller and located in a crowded region. And perhaps that is the deeper point. Pluto exposes the danger of oversimplified categories. The universe does not operate in neat tiers. There is no sharp boundary between asteroid and planet, between moon and world, between minor body and major object. Instead, there is a spectrum. Pluto sits somewhere along that spectrum. The debate over its status reflects our attempt to draw lines across a continuum. But nature rarely respects lines. Part 6 of Pluto's story is therefore about humility. For centuries, humanity believed Earth was unique. Then we learned it was one planet among many. For decades, we believed the solar system ended at Pluto. Then we discovered the Kuiper Belt. We believed Pluto was a massive hidden planet. Then we learned it was small. We believed it was frozen and inactive. Then we discovered glaciers and mountains. Each time, our assumptions were corrected, not because anyone lied, but because knowledge deepens. Pluto teaches us that small does not mean simple, that distant does not mean dead, that categories are provisional, and perhaps most importantly, that exploration changes identity. Before 2015, Pluto was a blurry dot. After New Horizons, it became a landscape, and landscapes are harder to dismiss than points of light. Pluto may no longer be the 9th planet in textbooks, but it has become something arguably more important. A symbol of how science evolves, a reminder that the edges of our maps are rarely empty, and proof that even the smallest worlds can reshape our understanding of the universe. Pluto is not what you think, not because it was misrepresented, but because it turned out to be far more extraordinary than we imagined. If Pluto has unsettled our definitions, reshaped our maps, and expanded our understanding of what small worlds can be, then this chapter must confront the final layer of the story. What does Pluto's journey reveal about us? Because in the end, the debate over Pluto is not just about astrophysics. It is about how humans construct meaning. When Pluto was discovered in 1930 by Clyde Tombaugh, it arrived at a particular moment in history. The world was between wars. Astronomy was entering a new era of precision. The idea of a hidden planet X had captured imaginations. Pluto was not discovered as a minor object. It was discovered as a solution, an answer to predicted gravitational anomalies in Neptune's orbit, though later calculations showed those anomalies were overstated. Pluto's identity was born as something grand. From the beginning, it carried narrative weight, and narrative matters. For generations, Pluto became a symbol of the frontier, the outermost world, the final planet, the edge of the known solar system. That symbolism embedded itself deeply in culture. So when its status changed, the emotional response was not irrational, it was human. We don't just memorize facts about space. We build stories around them. And Pluto's story shifted. But here's something subtle. Pluto was never removed from the solar system. It was never erased. It was recontextualized. That difference matters. In many ways, Pluto's reclassification reflects a broader pattern in science. Early discoveries often appear singular and isolated. As knowledge grows, those singularities become part of populations. When Uranus was discovered in 1781, it expanded the solar system. When Neptune was found in 1846, the outer boundary moved again. Pluto seemed to continue that outward progression. But instead of marking a new frontier, Pluto eventually revealed an entire region beyond Neptune. It did not extend the list of planets. It revealed a belt of worlds. This is not a demotion. It is an expansion. The solar system is not 8 isolated bodies with a few stray rocks. It is layered, inner rocky planets, outer gas giants, Kuiper Belt objects, scattered disk objects, Oort cloud comets. Pluto is the gateway between categories, and gateways are powerful. They challenge linear thinking. For decades, we imagined the solar system as a tidy sequence, Mercury to Pluto, a straight line of increasing distance. But reality is not linear. It is structural. It is populated. It is chaotic in places. Pluto disrupted the simplicity of the diagram, and diagrams are comforting. But diagrams are not truth. Another deeper implication of Pluto's story involves authority in science. When the International Astronomical Union voted in 2006, many people interpreted the decision as top-down, a small group deciding the fate of a beloved world. Yet science is not governed like a political system. It is a process of consensus building, evidence accumulation, debate, and revision. Definitions evolve. The word planet itself has changed many times across history. In ancient Greece, planet simply meant wanderer. It referred to any object that moved against the background of stars, including the sun and moon. Later, Earth joined the planetary ranks after heliocentrism replaced geocentrism. Then Ceres was called a planet, and later reclassified. Pluto's shift fits this historical pattern. We revise categories as understanding improves, but humans resist revisions when they disrupt memory. Pluto's reclassification occurred in the age of the Internet, an era where scientific decisions are instantly public, debated, and emotionally amplified. Had the change occurred quietly in the 19th century, it might have passed with little notice. Instead, it became global news. In some ways, Pluto became a symbol of scientific authority colliding with public attachment. And that tension reveals something profound. Science is not separate from culture. It operates within it. Pluto's journey from planet to dwarf planet forced people to confront how definitions are created. It showed that categories are tools, not sacred truths. But perhaps the most important lesson lies beyond the debate. It lies in exploration. Before New Horizons, Pluto was controversial but abstract. After New Horizons, Pluto was visible. You could see its mountains, its plains, its haze-layered atmosphere, its blue horizon. And once you see a world up close, its label becomes secondary. Whether planet or dwarf planet, Pluto is undeniably a world. It has landscapes, it has geology, it has seasons, it has history. The argument over terminology fades in comparison to the reality of its complexity. This is the transformative power of exploration. Labels may shape public discourse, but images reshape imagination. The heart-shaped Tombaugh Regio did more for Pluto's identity than any vote ever could. It gave Pluto character, and character transcends classification. There is also a philosophical dimension here. Pluto exists at the boundary between dominance and community. It does not rule its orbit, but it is one of the largest members of a collective population. Perhaps that metaphor resonates beyond astronomy. Pluto is not powerful in isolation. It is significant in context. It represents a broader family of icy worlds, many still undiscovered. Future telescopes may detect more Pluto-sized objects in the Kuiper Belt. Future missions may return to study them. And as we discover similar bodies around other stars, Pluto may become less exceptional, but more representative. It may be the prototype of a common type of world, and that possibility reframes everything. Pluto is not the smallest of the 9. It is the largest of the Kuiper Belt. Perspective changes identity. Part 7 of Pluto's story is not about winning the argument. It is about embracing complexity. The solar system is richer than we imagined in 1930. It is more crowded, more dynamic, more layered. Pluto did not diminish our understanding. It expanded it, and in doing so, it revealed something fundamental. The universe does not conform to the neat categories we prefer. It spills over them. It blurs boundaries. It forces revision. Pluto is not what you think, not because it was misclassified, not because anyone lied, but because discovery is always disruptive. And sometimes, the most distant worlds are the ones that teach us the most about how we define reality itself. By the time New Horizons sent back its final streams of data from Pluto, something subtle had already changed. The argument about whether Pluto was a planet suddenly felt smaller, not resolved, not settled, just smaller, because the images were undeniable. There were mountains made of water ice rising several kilometers high. There were frozen nitrogen plains shaped like enormous convection cells. There were signs of glacial flow. There were atmospheric hazes layered in delicate blue arcs above the horizon. This was not a forgotten rock. This was a world. And once you accept Pluto as a world, the debate shifts from terminology to trajectory. What happens next? Pluto's story is not finished. It has barely begun. New Horizons was a flyby mission. It raced past Pluto at nearly 50,000 kilometers per hour. The entire close encounter lasted only a few hours. The data it transmitted back to Earth took more than a year to fully download because of the enormous distance. We have seen only one hemisphere in detail. The other side remains largely mysterious. There could be features we haven't even imagined. Cryovolcanic regions, impact basins, seasonal frost deposits shifting over time, subtle atmospheric variations as Pluto moves farther from the Sun. Unlike Mars or Jupiter, Pluto has not been revisited. There is no orbiter circling it, no lander sampling its surface, no atmospheric probe diving through its thin nitrogen haze. And yet, the scientific questions surrounding Pluto have multiplied. Does Pluto truly harbor a subsurface ocean? Models suggest that radioactive decay inside its rocky core could produce enough heat to keep a layer of water liquid beneath the crust. Ammonia mixed into the water would act as antifreeze, lowering the freezing point. If that ocean exists, it might be sandwiched between layers of ice, insulated from the brutal cold of space. But how long could such an ocean survive? Billions of years? Or only in early history? Could there be fractures in the crust that allow material from the interior to reach the surface? The smooth plains of Sputnik Planitia hint at internal motion. The absence of craters in some regions suggests resurfacing within the last 100 million years, recent in geological terms. If Pluto is geologically active today, even slowly, it forces a reassessment of how small bodies retain heat. And that reassessment extends beyond Pluto, because in the outer solar system, there are many icy worlds. Triton, Neptune's largest moon, shares similarities with Pluto and may have originated in the Kuiper Belt before being captured by Neptune's gravity. Triton has geysers. It has nitrogen frost. It has a retrograde orbit. Studying Pluto helps interpret Triton, and vice versa. The Kuiper Belt itself remains largely unexplored. Thousands of objects are estimated to exist there. Many only faint points of light through telescopes. Some may rival Pluto in size. Others may be smaller but equally complex. Each one is a fragment of solar system history. Pluto, as the first close-up encounter with a Kuiper Belt object, is a template. It sets expectations, but it also warns us not to underestimate small worlds. Another question lingers in planetary science. Should we return? A Pluto orbiter mission has been proposed in various forms. Such a spacecraft could map the entire surface in high resolution. It could measure changes in the atmosphere over time. It could deploy a probe to sample atmospheric composition directly. But reaching Pluto is not easy. It requires nearly a decade of travel time. It demands precise gravitational assists and limited fuel budgets. It operates in an environment where sunlight is less than 1,000th as strong as on Earth. Solar panels are ineffective. Nuclear power sources become essential. The engineering challenges are enormous, and yet Pluto's scientific rewards may justify them, because Pluto is more than a distant world. It is a boundary marker. It marks the transition between the inner planetary system and the outer debris field. It sits at the edge of where planets end and primordial remnants begin. In some ways, Pluto is like a fossil embedded in rock layers. Studying it reveals the conditions of early planetary formation. The chemical composition of its ices, nitrogen, methane, carbon monoxide, preserves the chemistry of the protoplanetary disk. Its surface coloration, shaped by ultraviolet radiation interacting with frozen gases, shows how complex organic molecules can form naturally. Pluto may not host life, but it contributes to the story of how chemistry evolves in cold environments. And that story matters, because when we look at distant exoplanets, we will not see mountains or glaciers directly. We will see spectral signatures, atmospheric compositions, light curves. Understanding Pluto helps calibrate those interpretations. It teaches us what frozen nitrogen plains look like from afar. It teaches us how thin atmospheres scatter light. It teaches us how ice worlds behave over time. There is also something symbolic about Pluto's future. When the sun exhausts its hydrogen fuel, billions of years from now, it will expand into a red giant. The inner planets may be engulfed or scorched beyond recognition. The Kuiper Belt will warm. Pluto's frozen surface may temporarily thaw. Its nitrogen ice may sublimate completely. Its hidden ocean, if it exists, might expand. For a brief cosmic moment, Pluto could become warmer than it has ever been. Eventually, as the sun sheds its outer layers and shrinks into a white dwarf, Pluto will freeze again, orbiting a dim stellar remnant in darkness. Pluto's future is as dramatic as its past, and that perspective reframes the debate entirely. Planet or dwarf planet, it does not matter on billion-year timescales. Pluto will persist long after human categories are forgotten. Part 8 of Pluto's story is about continuity. Scientific understanding does not stop with one mission. It evolves. The same world that was once a blurry dot in 1930 is now a detailed landscape. The same world that was declared a planet, then a dwarf planet, now stands as a gateway to a vast region. And perhaps the final insight of this chapter is this: Pluto represents humility. It reminds us that certainty is temporary, that diagrams are provisional, that the universe is not obligated to match our expectations. Pluto is not what you think, not because it deceived us, but because every time we look closer, it reveals another layer. It is a small world with a long memory, a distant world with a complex history, and a reminder that the edges of knowledge are never empty. They are waiting. If Pluto has reshaped our definitions, expanded our models, and humbled our certainty, then this chapter must explore the final transformation. Pluto is no longer an exception. It is a prototype. For most of the 20th century, Pluto was viewed as an anomaly, a strange, distant object that didn't quite fit with the inner rocky planets. or the outer gas giants. It was an oddity, but the discovery of the Kuiper Belt changed that perspective entirely. Pluto is not unusual. It is typical. It is one of the largest members of a vast population of icy bodies orbiting beyond Neptune. These objects vary in size, composition, and orbital shape, but they share a common origin, remnants of the early solar system that never fully merged into larger planets. In other words, Pluto may represent the most common category of world in our solar system, and possibly in the galaxy. Think about that shift. For decades, we thought Pluto was the outermost planet. Now we understand it as the most accessible representative of an enormous hidden population. This recontextualization has enormous scientific implications because when we examine exoplanetary systems, the thousands of planetary systems discovered around other stars, we often see patterns that do not resemble our simplified 8-planet model. Many systems contain multiple small icy bodies in outer regions. Many systems contain planets that fail to dominate their orbits completely. Many systems contain worlds that sit between clear categories. Pluto may not be the exception. It may be the rule. The boundary between planet and dwarf planet might be more common than planetary dominance itself. And that forces a philosophical question. If Pluto-like bodies are common throughout the galaxy, does restricting the word planet to 8 objects in our own system make sense? Or does it artificially narrow our perception? This is where Pluto becomes less about classification and more about representation. Pluto represents a stage of planetary evolution that is often overlooked. It formed from the same protoplanetary disk as the larger planets. It accumulated mass through collisions. It heated internally. It differentiated into layers, but it stopped short of clearing its orbital zone. Why? Because Neptune's gravitational influence shaped its destiny. Neptune migrated outward early in solar system history. In doing so, it scattered and trapped countless icy bodies into resonant orbits. Pluto was caught in a 3-to-2 resonance. For every 3 orbits Neptune completes, Pluto completes 2. This resonance stabilizes Pluto's elongated path. Without it, gravitational interactions might have ejected Pluto from the solar system long ago. Pluto's existence in its current form is a product of planetary migration, and planetary migration appears to be common in other systems. Giant planets around other stars often sit much closer to their stars than expected, suggesting they moved after formation. If Neptune had migrated differently, Pluto's history would be entirely different. It might have collided with another body. It might have been ejected. It might never have formed as a distinct world. Pluto's identity is shaped by cosmic choreography, and that choreography reflects the chaotic early dynamics of planetary systems. Understanding Pluto helps scientists refine migration models. It helps constrain how giant planets move and how small bodies respond. But Pluto also tells us something about survival. In the early solar system, collisions were violent and frequent. Many bodies merged into larger ones. Many were destroyed. Pluto survived. It grew large enough to become spherical, but not large enough to be consumed. It represents a survivor of the solar system's most chaotic era. Survivors carry memory. The chemical composition of Pluto's surface preserves information about the primordial disk. The ratios of isotopes in its ices provide clues about temperature conditions during formation. Even its internal layering offers evidence of early heating and differentiation. Pluto is not just a world. It is a fossil record. There is also the matter of time. Pluto's orbit takes 248 Earth years to complete. Seasons on Pluto last decades. When New Horizons visited in 2015, Pluto was near perihelion, relatively close to the Sun in its elongated orbit. Its atmosphere was extended. Nitrogen ice was sublimating. As Pluto moves farther away, that atmosphere may partially freeze out. We are witnessing Pluto at a particular moment in a very long seasonal cycle. Future generations may observe different atmospheric behavior. Pluto evolves slowly, but it evolves. That dynamic quality contradicts the old image of Pluto as a frozen relic. It is not static. It responds to solar distance. It reshapes its surface. It exchanges material between atmosphere and crust. These processes occur on timescales far longer than human lifetimes, but they are real, and perhaps that is part of Pluto's lesson. The outer solar system operates on different rhythms, slower, colder, more subtle, but no less active. There is another deeper implication to Pluto's story. For centuries, humanity assumed that complexity required proximity to a star. Warmth meant activity. Distance meant death. Pluto challenges that assumption. Internal heat from radioactive decay can sustain geological processes even in deep cold. Tidal interactions are not the only source of energy. This expands the potential range of active worlds. And when we think about habitability, not just life as we know it, but environments capable of chemistry and change, Pluto widens the field. It reminds us that habitable zone is not a simple ring around a star. There are hidden oceans beneath ice. There are chemical reactions driven by radiation. There are processes that do not require sunlight. Pluto may not be habitable, but it reshapes the map of possibility. Part 9 of Pluto's story is about perspective. It is about recognizing that Pluto is not a mistake in classification. It is a bridge between categories. It connects planets to debris. It connects geology to ice. It connects migration to survival. It connects early chaos to long-term stability. Pluto was once thought to be the outermost planet. Now it is understood as the inner representative of a vast unseen region. That shift is not a downgrade. It is a revelation. Pluto is not at the end of the solar system. It is at the beginning of something larger. And perhaps the greatest irony of all is this. The world we thought was the smallest and least significant may turn out to be one of the most scientifically important. Not because it fits our definitions, but because it challenges them. Pluto is not what you think. It is not the 9th planet. It is not just a dwarf planet. It is a key to understanding how planetary systems form, evolve, migrate, and survive. And keys are rarely large, but they unlock everything. If Pluto has transformed from planet to dwarf planet, from anomaly to prototype, from distant dot to complex world, then this chapter must confront the final question. What happens to Pluto's identity in the long arc of cosmic time? Because classifications are human, but evolution is universal. Pluto's story does not end with its current orbit, its present atmosphere, or even our era of exploration. It stretches billions of years forward. Right now, Pluto orbits the Sun at an average distance of nearly 6 billion kilometers. Its elongated path carries it from about 30 astronomical units at perihelion to nearly 50 astronomical units at aphelion. That wide range means Pluto's environment changes dramatically over centuries. When closer to the Sun, nitrogen ice sublimates, forming a thin atmosphere. When farther away, the atmosphere can partially freeze and fall back onto the surface like frost. This slow breathing cycle may continue for millions of years. But the Sun itself is not constant. In about 5 billion years, the Sun will exhaust its hydrogen fuel and begin expanding into a red giant. The inner planets, Mercury and Venus, will likely be engulfed. Earth's fate remains uncertain, but it may be scorched or swallowed as well. As the Sun expands, its luminosity will increase dramatically. The Kuiper Belt will warm. For the first time in its history, Pluto may experience significant heating from stellar radiation. Its nitrogen and methane ices could sublimate extensively. Its atmosphere may thicken temporarily. Its surface could transform. If Pluto harbors a subsurface ocean, increased heat might expand that liquid layer. For a brief cosmic moment, Pluto could become more active than ever before. But this phase would not last long. As the Sun sheds its outer layers and collapses into a white dwarf, its energy output will decline sharply. Pluto will once again freeze, this time orbiting a dim stellar remnant in near total darkness. Its nitrogen atmosphere may permanently escape into space. Its surface may stabilize into deep cold. Its geological activity, already slow, may cease entirely. Pluto will become a frozen relic orbiting a fading star, and long after humanity is gone, Pluto will still circle that white dwarf every 248 years. Its label will not matter. Its existence will. This perspective reveals something profound. The debate over Pluto's planetary status occupies a few decades of human time. Pluto's orbital history spans billions of years. The controversy is microscopic compared to the lifespan of the world itself. And yet, that controversy reflects something uniquely human: our need to categorize. Pluto challenges that instinct. It reminds us that categories are temporary scaffolding. The universe operates on scales beyond them. There is another aspect of Pluto's long-term future that intrigues scientists. As the Sun loses mass during its red giant phase, gravitational dynamics throughout the solar system will shift. Planetary orbits may expand. The Kuiper Belt could become destabilized. Some objects might be ejected into interstellar space. Could Pluto remain bound to the Sun's gravity? Most models suggest yes, but its orbit could widen significantly. It might drift farther out, becoming even more distant. Or gravitational interactions could alter its path unpredictably. Pluto's stability is not guaranteed over cosmic timescales, and this possibility reframes Pluto yet again, not as a permanent fixture, but as a dynamic participant in the evolving solar system. Part 10 of Pluto's story is therefore about impermanence, not of Pluto itself, but of certainty. When Pluto was discovered, it was believed to be massive and possibly responsible for gravitational perturbations. That belief changed. When Pluto was labeled the 9th planet, that classification seemed permanent. It changed. When Pluto was thought to be inert, that assumption shifted after New Horizons. Science updates itself, and so will our understanding of Pluto. Future telescopes may detect geysers erupting from its surface. Future missions may measure gravitational anomalies, hinting at a liquid ocean beneath. Future models may refine or overturn current theories of its formation. Pluto will continue to surprise. There is also something poetic about Pluto's name. In Roman mythology, Pluto is the god of the underworld, ruler of hidden realms. Fittingly, the real Pluto presides over the hidden region of the Kuiper Belt, a distant kingdom of icy worlds. It is not a lonely exile. It is part of a vast unseen domain. And that symbolism deepens when we consider humanity's relationship to the outer solar system. The Kuiper Belt remains largely unexplored. Most of its members are too small and faint for detailed observation. Pluto is our first ambassador from that realm. It is the first world from that hidden region to reveal its face in detail. And what it revealed was complexity, mountains, glaciers, haze layers, possible oceans. The underworld was not empty, it was alive with structure. There is one final philosophical dimension to Pluto's story. When something changes classification, people often interpret it as a downgrade. But in science, reclassification is not punishment, it is refinement. Pluto was not demoted out of irrelevance. It was redefined in light of new context. And context is everything. Without the discovery of Eris and the broader Kuiper Belt, Pluto might still be considered the ninth planet. But that would obscure the true architecture of the solar system. Pluto's new identity places it within a population. It acknowledges that it is not alone. In a way, Pluto's reclassification mirrors humanity's own journey. For centuries, Earth was believed to be the center of everything. Then it became one planet among many, then one world among billions of stars. Each shift felt destabilizing. Each shift expanded perspective. Pluto's shift is part of that same pattern. It reminds us that our understanding is always provisional, that maps are redrawn, that edges become gateways. Pluto is not what you think. It is not simply the ninth planet. It is not merely a dwarf planet. It is a witness to solar system formation, a survivor of early chaos, a representative of a vast unseen population, a world that breathes nitrogen frost and hides potential oceans beneath ice. And long after debates fade and textbooks change again, Pluto will remain, orbiting quietly in the darkness, indifferent to the words we use to describe it. Because in the end, Pluto does not need a title. It needs only to exist. An existence in the cold silence of the Kuiper Belt is enough. By now, Pluto is no longer just a reclassified object in a textbook. It has become something else entirely. It has become a mirror reflecting how we think about science, authority, discovery, and the limits of certainty. Because when people say they lied to us about Pluto, what they often mean is something deeper. They mean, why did the story change? And that question deserves an honest answer. The story changed because knowledge expanded. But expansion can feel like contradiction. When Clyde Tombaugh discovered Pluto in 1930, astronomers were searching for a large hidden planet whose gravity was thought to be tugging on Neptune and Uranus. Pluto was smaller than expected, but it was the only object found in that region at the time. In isolation, it looked like a planet. At that moment in history, it made sense. But science does not freeze in time. By the late 20th century, better telescopes revealed more objects beyond Neptune. Then came Eris, slightly more massive than Pluto. Suddenly, astronomers faced a dilemma. If Pluto was a planet, then Eris must be one too. And if Eris was a planet, then so might be Makemake and Haumea, and possibly dozens more objects still undiscovered. The solar system was no longer a neat ladder of 9 steps. It was a crowded outer region filled with similar-sized icy bodies. The definition had to evolve, not because Pluto shrank, not because someone deceived us, but because Pluto was no longer alone. And here is the uncomfortable truth. Most scientific revolutions feel like contradictions when they first occur. When Earth was removed from the center of the universe, it felt like a loss. When Newton's physics was replaced by Einstein's relativity, it felt destabilizing. When dinosaurs were discovered to be more bird-like than reptilian, it disrupted long-held images. Science refines itself. It does not cling to earlier versions for comfort. Pluto's story is part of that refinement. But there is another layer here, one that goes beyond astronomy. Pluto's reclassification revealed how attached we become to simplified models. For decades, the solar system was taught as 9 planets orbiting the Sun in tidy sequence. It was easy to memorize, easy to visualize, but the real solar system is not tidy. It is layered and chaotic. Between Mars and Jupiter lies the asteroid belt, thousands of rocky bodies, including Ceres, which was once considered a planet. Beyond Neptune lies the Kuiper Belt, thousands of icy bodies, including Pluto. Farther still may lie the Oort cloud, a spherical halo of cometary debris extending nearly a light year from the Sun. The solar system is not a clean list. It is a gradient. Pluto sits at the transition between planet and debris, and transitions are uncomfortable. They blur boundaries. They resist categorization. That is why Pluto matters. Not because it is large, not because it is dominant, but because it occupies the gray area. Gray areas are where science grows. When New Horizons flew past Pluto in 2015, it did not resolve the classification debate. It intensified it because the images showed undeniable complexity. The heart-shaped Tombaugh Regio, the nitrogen glaciers of Sputnik Planitia, the towering mountains of water ice, the hazy blue atmosphere stretching into space. Pluto looked like a world, not a leftover fragment. And that visual reality collided with its official label. How could something so dynamic not be a planet? The answer depends on what we value in the definition. If dominance defines a planet, Pluto fails. If complexity defines a planet, Pluto qualifies. And here lies the core of the disagreement. Is a planet defined by its role in orbital hierarchy, or by its intrinsic physical properties? There is no deception in choosing one framework over the other. There is philosophy. The International Astronomical Union chose orbital dominance. Many planetary scientists prefer geophysical complexity. Both perspectives are defensible. Neither is malicious. The phrase, "they lied to us," reflects emotional frustration, not factual deception. Pluto was called a planet because it fit the knowledge of its time. It was reclassified because new discoveries demanded reorganization. This is not betrayal. It is revision. And revision is the heartbeat of science. Part 11 of Pluto's story is therefore about trust. Trust in the process of inquiry. Trust that categories may shift without undermining reality. Pluto's mountains did not disappear in 2006. Its glaciers did not vanish. Its atmosphere did not thin because of a vote. Only the label changed. And labels are tools. There is something else that Pluto reveals about us. We often mistake simplicity for truth. 9 planets felt complete. 8 planets feels clean. But the solar system is neither simple nor clean. It is messy, populated, dynamic. Pluto exposed that messiness. And perhaps that exposure is what unsettled people, because once you accept that Pluto belongs to a vast outer population, you must accept that the solar system is more complex than a row of spheres. Pluto forces us to expand our mental map, and expanding maps requires letting go of older diagrams. In the end, Pluto is not diminished by its reclassification. It is elevated by its context. It is the first close-up ambassador from the Kuiper Belt. It is a case study in planetary thresholds. It is evidence of migration, resonance, survival. It is a world that breathes nitrogen frost and hides potential oceans. Whether you call it a planet or a dwarf planet, it remains extraordinary. The deeper lesson is this: science does not protect nostalgia. It protects accuracy, and accuracy evolves. Pluto is not what you think, not because anyone lied, but because the story grew larger than the original category could contain. And when stories grow larger, definitions must stretch or break. Pluto did not break, it expanded, and in doing so, it expanded us. Pluto began as a prediction. It became a discovery. It turned into a planet. Then it was redefined. And now, after nearly a century of observation, argument, and exploration, Pluto stands not as a mistake, not as a downgrade, but as a turning point. Because Pluto's story was never really about size. It was about perspective. When Clyde Tombaugh first identified Pluto on photographic plates in 1930, he had no idea what he had truly found. No one did. It was simply the next object beyond Neptune, a faint moving speck against the fixed stars. For decades, that speck carried enormous symbolic weight. It was the edge, the last world, the frontier. But frontiers move, and every time they move, our categories are forced to move with them. Pluto's reclassification in 2006 did not erase its past. It recontextualized it. It acknowledged that the solar system is not composed of a tidy row of 9 bodies separated by empty space. It acknowledged the Kuiper Belt, a vast population of icy worlds that had always been there, waiting to be seen. Pluto did not shrink when we found its neighbors. It simply stopped being alone. And that is the heart of the matter. Pluto was once exceptional because we believed it was singular. When we learned it was part of a larger family, we had 2 options: expand the list indefinitely or refine the category. Astronomers chose refinement. Some disagreed. That disagreement continues. But disagreement is not deception. It is evidence that science is alive. The deeper truth is this: Pluto forced us to confront the limits of our definitions. The word planet feels ancient and permanent, but it is neither. It has shifted throughout history. It once included the sun and moon. It once excluded Earth. It once included Ceres. It evolved, and it will likely evolve again. Pluto revealed